Welcome back. So we had this beautiful session on symmetries in the morning. So now we will raise the stakes a little bit and become supersymmetric. So the first speaker is Pedro Vieira.
Very good. Thank you very much. Thank you very much, Ahmed, and everyone in the organization of this spectacular conference. So, I mean, at least we are just starting, but I think I've never been in a conference with more than one banner, so and I could even tell my Uber driver, it's here for sure, yeah. I don't know. Solid cubes, I checked. These cubes are really solid, so it's really quite impressive, yeah? Very good. So maybe we could put my slides up. Sorry. The slides are not up. They are. Very good. Oh, thank you. Yes. So I'm going to talk about a recent paper that we wrote with Arish Murali, who is in the audience, and Volodya Kazakov, on trying to understand huge operators. Huge operators are operators for which back reaction is important, and I'm going to review briefly what I mean by huge operators, but these are operators that you act on them with your system and they change your vacuum. The back reaction is important. And we'll be studying correlation functions of these very heavy operators and try to understand how a SCFT and how holography could work in the presence of these big operators and what could you predict for such interaction of big operators in n=4 super Yang-Mills dual to ADS5. Okay, very good. So just to set the stage, of course, this list of references is by no means extensive, but operators could be distinguished very broadly into light, heavy, and huge. Okay, so light would be quantum operators, like a graviton, a photon, something very light that travels following all quantum trajectories, and we would have to compute Witten diagrams, and we would have the boundary of ADS, and we study some interactions, and we integrate over that, where that happens, and a lot is known about such operators, and of course, these lines could be, again, particles or very light strings. Then we have heavy operators, but not yet huge. They would be the so-called heavy operators in the middle, whose dimension is very big, and because the dimension is very big, these processes of propagation effectively become classical. We can have, for example, a very big string, so a very big string follows a classical trajectory, or a D-brane, whose dimension is of order n, and it would follow a classical trajectory. And then, and those would be described by a process like that, where we would have some process in the bulk, where I would have 3 points where I insert these very big strings. I send these very big strings. They could be strings with very big charges, and therefore they are heavy. Or they could be strings with small charges, but very big string tension, and so there would be some string excited states. And then we would have a picture, okay, like the one in the middle. We could also have operators which are even heavier than D-branes. They would have dimensions of order n square. So they are so heavy that they are enough to back-react the geometry. Then I represent this object, like this octopus, I like to call it this three-legged banana, where the geometry is not ADS. The geometry is ADS far away from this object, but as I approach this object, back-reaction is important, and as I approach the core of this object, or the tentacles of the object, the metric would be deformed, the geometry would be deformed, and I would need to find the geometry that merges together 3 geometries coming from 3 different points and merging together in a complicated way. Okay? Now, then I can also do mixed stuff. I could do heavy stuff with light stuff, and in particular, people love studying these heavy light kind of objects. They are a bit easier to study. So these guys, you should think that by putting, say, a huge light, the huge operator creates a background, and so huge light is the same as a light operator, but now not in ADS, but in the new geometry. So these operators are very useful probes of ADS-CFT, because you can put these operators and do precision tests. You can say, does it work? Do I change the geometry to what I think? Let me measure this supergravity mode in this new geometry and see if it works. And these correlators, these heavy light correlators, they are order 1 quantities. They are not exponentially suppressed or exponentially enhanced. They are the expectation value of probes in the presence of a new geometry or in the presence of ADS plus some classical big object that is there. So I'm saying this to contrast with the case of 3 heavy objects. So 3 heavy objects is a different beast altogether. That correlation function is exponentially behaving. So that you should think is like a tunneling process, where you send an operator that needs to decay into two big operators. So it's a very violent process that you have this universe, one geometry comes from one leg of the octopus that splits into two. So this geometry is very different from the two-leg geometry. I would call this the regular banana, and the other one the three-legged banana. And the three-legged banana is not the same or built easily from the two-legged banana, of course, right? In the same way that the geometry for a black hole merger is much more complicated than the geometry of a single black hole, right? Okay, very good. Now, somehow these geometries, here I have the boundary of ADS, and this represents a two-point function of an operator that is so heavy that the geometry is deformed, and we call this some kind of space-time bananas. The two-point function is relatively easy to study. If I know what background this operator generates, then I know how to describe this background, say, in global ADS, where I have, for example, a black hole or some geometry that is there from minus infinity to plus infinity. And roughly speaking, what you have to do is map minus infinity to a point in the boundary and map plus infinity to another point, and then you are more or less done. You have to do a few weak rotations and so on, but basically that's it. Whereas for 3 points, that's not the case. 3 points, we no longer have just plus and minus infinity. We have 3 points, and we have this merging, and things are, of course, richer and more complicated. And so that's what I would like to describe today. Now, what we are going to do is study this in the context of n equals 4 super Young mills and heavy operators that are so-called 1/2 BPS operators. So let me review what they are. So this is the definition up there. So I have an operator which is just the trace of one of the complex scalars of n equals 4 in a given representation R. That's it. So let me just decode that notation. So trace in a given representation is called character. That's what that chi stands for. And R is a representation. So a representation is given by a Young tableau. For example, here I drew a Young tableau, and as an example with 4 boxes. Okay? Good. So then Y is a null vector. Phi are the 6 scalars of n equals 4. So Y dot phi is one of the complex scalars. So that's a matrix phi, which has eigenvalues Zi. And then very explicitly, in terms of those eigenvalues, this character is just the determinant written there, where lambdas are how many boxes there are in row number j. That's what lambda j is. And that combination, lambda j slightly shifted, will show up a lot. It's called hj. It's like the shifted Young tableau. It's the Young tableau where you add to it j minus 1, so you add to it this blue triangle. So you see here in this picture, the representation is a square. The shifted representation is this triangle with this Tetris shape at the very end. And if you just take this definition of the operator as an exercise, you plug this definition, the eigenvalues, you compute this character, and you get the expression there. It's a pity this pointer, I cannot point. And as you see, it has a bunch of traces, right? As we know this, so this is an example of a light operator. It would have dimension 4 in this example. There are 4 scalars. So here, I'm still describing generic operators. This one is light. And if you look at it, you see, for example, the last term is trace of phi square square. Trace of phi square, normally we think of it as a small string. So trace of phi square square is 2 strings. Okay? So this would be an example of an operator that, roughly speaking, you can think of it as a combination of 1 and 2 strings. But then as you put more and more boxes, you would get bigger and bigger operators, and eventually you have a big gas of many, many, many strings that are so big that back-react the geometry, and they change the geometry into some geometries that Lin, Lunin, and Maldacena studied. Okay? So I have here a few important comments. First, correlation functions of these operators do not depend on the coupling. Because of supersymmetry, these correlation functions, you can compute them just doing weak contractions at 0 coupling. So all you have to do is you take 3 of these characters and you weak contract them. So it's a purely combinatorial problem. There are no vertices, no integrations over vertices, nothing. It is just combinatorics of these weak contractions between these 3 operators. This is a nice basis of operators. The reason I like them very much is because they are orthonormal. They form an orthonormal basis. So different representations have 0 2-point function. So it's a nice basis of operators. It was a very important test of ADS-CFT in the beginning of ADS-CFT that this correlation function that was coupling independent was matching between weak and strong coupling. And as I wrote in the previous slide, There has been lots of work on light operators, some work on heavy operators, and not as much work on huge operators, which is what I'm describing today. Okay, very good, but for now, so what would be these huge operators? These huge operators would be operators where I have these big Young tableaus, big representations, where each line has order n boxes. So in total, I have order n square boxes. And here are just a few examples. So the Young tableau could be a square or a rectangle in red. And then the shifted Young tableau, when I add this triangle to make these h's, would be that. And in this case, this Young tableau there on the upper right corner, I would describe it by some density of these h's. And in this case, this density, for example, is constant between 1 and 2. Or I could have some other shape where the density is some smooth curve between a third and 3 plus a third, something like that, like in the bottom. And so the question is, what is the three-point function for big operators? In other words, what's the three-point function as a functional of these three densities for one operator, another operator, and the other operator? How do we find it? By solving this combinatorial problem of computing all these weak contractions between the three operators. Okay, so that's what I would like to describe. Okay, so the starting point, for now, we are going to take a step back and forget about huge operators. Let's do any size of operator. Then we will take the limit when the operators are big. So for now, it's more general. The representation can be whatever we want. So this is the starting point. Immediately, we can write that what we want to study is this three-matrix model. So indeed, it's obvious that it is this three-matrix model. What am I doing here? I'm putting a matrix model, Z, that depends on three representations, R1, R2, R3. And I'm inserting three characters, chi R1, chi R2, chi R3. And then I'm putting a kinetic term that is designed so that the propagator between M1 and M2 is 1, but between M1 and M1 is 0. In other words, this propagator just allows for contractions between different fields, but not the same field. Okay? So this is the type of matrix model that people studying the Potts model on random lattices and so on would use. Okay? So this is a propagator such that Mi, Mj is 1 if I is different than j. Now, as you see, this starting point, we have 3n squared degrees of freedom because we have three matrices. So even though it's coupling independent, it's a very complicated problem to compute this, to do this integral. So the first step when we deal with a matrix model is to try to reduce the degrees of freedom, which are order n squared, to something of order n. And this, it's almost trivial to do, because you see, almost everything depends on the eigenvalues of the matrix. The characters depend on the eigenvalues of the matrix. Trace of n squared depends on the eigenvalues of the matrix. Only this last term is annoying us a little bit with the coupling. But that one is trivial to resolve. We just introduce a new matrix X, well, something like X minus sum of the matrices square. And that will basically factorize the integrand into something of M1 times something of M2 times something of M3, where that something contains exponential of X dot M. So all I need to do is integrate the angle between X and M. By the angle, I mean you can write X as diagonal matrix, M as diagonal matrix, but then there is a matrix, a conjugation matrix between the two that I can integrate out. And when I do, I get something just in terms of the eigenvalues of X, M1, M2, and M3. And so we have a representation with 4n variables instead of 3n squared. And this is the final result of this procedure. Okay, so this expression so far, I emphasize, it's true for any operators, big, small, whatever you want. So we have a bunch of ingredients. Let me already highlight the important stuff. So first, there are some i's there, which are these Harish, Chandra, Itzik, and Zubair integrals. They are some simple determinants. And there are 6 of them. Why 6 of them? Because remember, we had 3 characters, and each character was a determinant, basically. So 3 of them are already there from the get-go. And then we have 3 new ones, because when we integrate the angle between each matrix M and X, we generate this I here, as you see in this line written here. Okay? So we have 6 I's, 3 from the characters, 3 from the integration over the angle between matrix M and X. Then we have the usual matrix model measure with a bunch of van der Monde factors and some Gaussian factors. That's easy. And that's basically it. So as you see, now this is very much ready for taking a large n limit. Now in the large n limit, the idea is that the action that we are integrating over is of order n squared, but we have n degrees of freedom, so this is given by a saddle point computation. Of course, the tricky thing is that we need to know how do I take the large n limit of the object there in the middle of this type of determinant. And as I will tell you in 2 slides, this was a problem that Matizin beautifully solved like 20 years ago. 30. Yeah, 30. Okay, but in a picture, let's summarize. We have these 6 m's. So you see that these m's connect the external h's with m's and x with m's. So this is the picture that represents the formula that I wrote there. So there are 4 types of integrations, eigenvalues x, m1, m2, m3. And then there is a propagator between h's, which were the Young tableau of operator 1 and m1, h2 and m2, h3 and m3. Those came from the characters. And then propagators between m3 and x, m2 and x, m1 and x, where by propagators I mean that these lines represent these Itzig and Zuber determinants, I between eigenvalue x and them. Okay? So far so good? So this is general. It's valid for operators of any possible size. But now it's easy to take the classical limit. The classical limit is the limit where all these quantum integrations localizes into some classical configuration where I don't integrate over the eigenvalues m, but I go to the saddle point, to the optimal configuration of m and x. And so all I need to do is find what is the classical limit of this determinant of exponential of xi yj. Okay? So imagine you have a determinant where the elements of the matrix are exponential of xi yj, where xi is a list of values and yj is another list of values that are given by some densities. So you would think, if you look at this for the first time, that you take a few log determinants and that it's a trivial result, but actually it's not. It's a very beautiful result, which I'm summarizing here. The claim is the following. Remember the definition of I. It's in the upper right corner. I is a trivial factor. The only factor that you should look at is the determinant. Forget about the rest. The rest is all trivial. But you have this determinant of exponential of n and then ai bi. So it looks like a trivial thing. There is a density for the a's, a density for the b's. How do I study this classical limit? And yet, the result is very beautiful. The result is that this determinant is given by exponential of n squared times the action of a fluid. It's a fluid in 1 + 1 dimension. It's an inviscid fluid whose action is given here. So you see the pressure is minus rho squared. This is the velocity of the fluid. And what we are instructed to do is the following. Suppose you start with some fluid, you want to compute that object I, where A's have some density rho A, and B's have some density rho B. Then you have to find a fluid that evolves from an initial density rho A to a final density rho B in 1 unit of time. So you see, rho A could be, for example, some parabola like here, and rho B could be some constant density like there, and then I would need to find this fluid that goes from one end to another. You see, it's a global problem. It's a problem in fluid dynamics where we are given the initial and final density. We are not given the initial density and velocity. Now, what's beautiful about this fluid, or one of the beautiful things about this fluid, is that this is an integrable model. It's given by the so-called Riemann-Hopf equation, and it's a model that is integrable. And by integrable, I mean that some things are very easy to study. For example, the direct evolution, when I know the initial density and velocity. Not everything is easy to study. Okay, very good. So then, with this result, immediately we can write what is then the result for the correlation function of 3 very heavy operators. And the answer is, it's given by a bunch of fluids. Like you have 6 pipes, and you have a fluid going from H1 to M1, and then from M1 to X, and you have another pipe. So you have these 6 pipes that are connected, and there is a condition at each junction of the pipes, which are the conditions in the bottom that are just the saddle point equations that tell you the variation of X and M should be extremum, and they tell you that, for example, the last line tells you the velocity as you enter that M1 pipe, and then you get a kick, and the velocity gets a small kick and gets changed a little bit. And the first equation, you see, tells you that the density of the fluid in the middle, the integral of the density in the fluid of the middle, is equal to 2x plus the sum of the velocities as they join in the middle. Okay? So that's a condition that you have to impose. And so that's the final result. You need to start with 3 densities, rho of H1, rho of H2, rho of H3 at the end. You have these conditions, these gluing conditions, and you have to find the global configuration of the fluid that describes this evolution. and then compute its action, and that's the result of the 3-point function. Okay, very good. So let's give an example. Suppose for an example that we do something a bit in reverse. So that's what we should do, is given 3 densities, rho 1, rho 2, rho 3, find this problem. But let's do something much easier. Let's suppose the 3 operators are identical, and suppose I take some row in the middle, row of x that I like. For example, I say row of x is just a semicircle. Then you see, if the operators are identical, I go to this equation here, and I compute rho, because I pick rho, and the velocities are all the same, so I know the velocity is 1/3 of whatever I compute. And now, in the middle, I know rho, because I picked it, and I know the velocity. And as I told you, if you know the velocity and the density, these fluids are trivial to evolve. And so that's what you can do. You can start with a semicircle rule, evolve this fluid. This is a fluid with negative pressure, so you see the particles are approaching each other. These particles, when I'm saying particles, it's because this fluid admits a beautiful discretization in terms of another integrable model called the rational Collegero-Moser model. And then this fluid, these particles of the fluid, they approach, and then they go into the next tube, so they are coming from the middle. Now they go to the next tube, that's the second picture. A shock wave forms, so they hit each other, they go complex, they go to the complex plane, the density becomes complex for a while, and then it becomes real again, and it goes at the end to some density of H at the end, and then I see what Young tableau did I study. Okay? And then we see that it was this Young tableau here at the bottom. Now, of course, so this is an example where now I learned what is the 3-point function for 3 huge operators with this Young tableau. Of course, that's not ideal. This is not what we wanted. What we wanted is not to start from the middle and then pray that I get something reasonable. I want to choose 3 Young tableaus at the end. But this is also possible. It's a bit harder, but it's possible to solve. Actually, numerical is very hard. When we were studying this, we were learning this, there was a beautiful review by Govin Menon, and he explains how this global problem is so hard to solve, and he explained some attempts to solve it numerically. But basically, we managed to solve this problem, and so we can basically start with some fluid that we understand well, like the one I showed you, and then adiabatically deform towards the fluid that we would like to study. And so, for example, here is an example of a flow starting from the middle and going to the ends, if we wanted to study some simple Young tableau corresponding to a trapezium, for example. And so you would have the particles, they start colliding, they form this shock wave, so the density becomes complex, and then goes into the next chamber, then they collide, they form this zipper-like structure, and they collide, and they go beautifully between 1 and 3 equally spaced, which is the density that you should get for a trapezium. Okay, very good. So we found some integrability in perhaps somehow unexpected corner. We are very used to integrability when we describe single strings, because the worldsheet of the string is integrable. So if I were to tell you I found integrability in studying a 5-point function in the planar limit, you would say, yeah, that's not so surprising. The worldsheet is integrable, so why not? Here we are finding integrability in describing a gas of a gazillion of gravitons and geometries and so on. So I don't think it was obvious at all that this integrability, this gift that we find this integrable model, this Riemann-Noth system, or the Collegero-Moser model, I think this was a priori, at least for me, not expected. We did not exploit its integrability to the fullest. Right now, what I'm telling you is, if you give me 3 densities, find the full flow, evaluate the action of the flow, and that's the 3-point function. It would be even better if you did not need to find the flow. If you could find a trick that given 3 densities, here is the result. That's how integrability would be really powerful. And indeed, in the context of 3 heavy operators that I mentioned before, when people were studying these minimal surfaces that end on 3 strings, indeed, the way we were to compute the minimal area for those surfaces, we would try to compute the area exploiting integrability without computing the shape of the surface. And this was very successful in works of gluon scattering amplitudes and so on, for example. Well, I think I've written what you all know how to read. So maybe just one thing that I would stress is that the result that we find is pretty much the opposite of universality, right? So you give me 3 different densities, and I tell you what the result is, right? So you give me some semicircle rules that you want for h's, and I tell you this is the 3-point function. And of course, when we speculate at night about black holes and so on, we say black holes, they should have huge amount of universality, microstates should not matter, they give me some very excited state, and the details of the microstate should not be very important, and so on. And of course, there's no contradiction between the two, because these are very special geometries, these are very special operators that are dual to geometries that don't have horizons, and that indeed are described by different Young tableaus correspond to different geometries. But ultimately, what we would like to do is to use combinatorics and field theory, which is combinatorics definitely a very well-studied subject in science, to learn about quantum gravity and the measure of quantum gravity and so on, which are very speculative topics, and in particular about how to deal with quantum black holes. And we are starting as a first step from what I told you, which is 3 1/2 BPS operators. So how do we go in this direction of going towards understanding black holes and big operators that will be dual to black holes? Well, first we should accept that eventually we'll do numerics, of course. It's not going to be beautiful analytics with some rational collegial Mosers. That's fine. But maybe the first step, while we could still do some analytics, would be to reduce a little bit the supersymmetry. And if people have ideas, we would for sure be very happy to discuss. Thank you.
Any questions?
So two questions. First of all, where did you use that you're using half BPS states other than 1/4 BPS? Because it seems like you're solving a representation theoretic problem. And second question is, how did you get those MI, M1, M2, M3 points from the effective quantum mechanics problem?
Sorry, I'm not sure I got the questions. So the first question was, if I know how to describe 1/4 BPS operators in the same way that I know how to describe 1/2, in terms of characters, for example?
Yeah, where did the 1/2 BPS information go in?
The 1/2, in fact, here you see that I used one scalar, which is this y dot phi. That's one complex scalar. Now, any function of that complex scalar is half BPS, because I just use one complex scalar. So characters is a nice basis because it gives you an orthonormal basis. But you could write exponential of trace of any potential of phi. So that if you write operators that are just made of one of the complex scalars, that's half BPS. So for example, 1/4 BPS, you could write them using 2 scalars instead of 1.
I see, thanks.
And they are much more complicated to describe. You had another question, which was?
Yeah, where did the M1, M2, M3 points come from in the effective quantum mechanics problem?
Sorry, the M's are just the H's. It is just, you see, this determinant is z to the power h, which is basically exponential of h times log z.
Okay.
Okay? And that's where you see h times log is the I that is there. M is just h. Sorry, I changed. It's just that h is of order n, so we wrote h equal n times small m.
Okay, thank you.
Yeah.
Thanks for a nice talk here. There are some resemblances to the topological vertex where you have also 3 representations, Young diagrams, and you get a correlation between them. In that case, it also is related to the matrix integrals. So the similarities are interesting. It could be coincidence. I don't have any direct reason they should be related. But also in analogy with that, there's also generalization. That one has periodic eigenvalues. So there's a Q-deformed version. Is there such a thing here also, where you have a Q-deformed version? And do you see any relation? Have you tried to connect this with topological vertex?
No, I did not try. No, I will explore that. Maybe I will ask you for the precise reference later. And about trigonometric version, no, I would not see. Yeah, I remember these trigonometric versions sometimes appear in ABJM, right? In some matrix models that appear in ABJM. Yeah, I can say that one of the things we tried was to think if this would generalize to ABJM, and it's very hard, so we failed. So maybe there will be something like that.
I'm missing something basic. In the starting point, I didn't understand if we were assuming G squared n is small so that we get this free field contractions.
Yeah, it's just that these 3-point functions are coupling independent. So the coupling doesn't matter.
I see. Thank you.
So it's only a function of n.
Thank you.
So in practice, you can compute them just at g equals 0.
Okay.
That would presumably not be true with less supersymmetry.
That's right.
Turning the last question.
Yeah. I think one half, 1 quarter. So one operator being 1/4 and 2 being 1/2. Sometimes it's still protected. But for sure, 1/4, 1/4, 1/4 would not be. It would still be very interesting to compute it and see what would happen with the loop corrections. Maybe we would get at 3 levels some integrable structure, and then the fluid would start breaking integrability as we go to loops or something.
Hi, Pedro. I was trying to count supersymmetries. So each operator that you have preserves 24 of the 32 supersymmetries because all S's and 8 of the Q's. And so if you put them all together, the whole configuration, does it preserve 8 out of the 32 supersymmetries? So when you're looking in supergravity, are we looking for solutions that preserve 8 supercharges for this configuration?
Yeah, Leonardo once told me the answer to this. Is it yes? I think so, but yeah, sometimes I think I do the mistake of thinking that it's 1/2, 1/2, 1/2, so I just multiply and I get 1/8, but that's a bit too fast because I can align the 2 operators, one to be Z, one to be Z bar, and the other one. So I think it's a bit more than, so it's more than 1/8. I thought it was 1/4, but.
So yeah, 8 out of 32 would be 1/4, yeah.
Very good, okay, then it makes sense. Cool.
Okay, one last question there.
Just a quick question. So if I wanted to ask about the old question of heavy, heavy, light, but say where the 2 heavies are not the same, does this help you at all?
Yeah, so if the 2 heavies are not the same, typically, well, often you cannot have this correlator, right? You have this Landau-Wigner transitions, or I don't know, something that people know well, that when you have 2 states that are too different, you cannot induce a transition between the 2 with a light operator. But if you can, then this would be of the same type that we compute here. So we could do, for example, 2 heavy operators, 3 huge operators, but 1 much lighter than the other 2, for example. Yeah, so that you could do. And it would be a degenerate case of this case. So it's something that studying the limit of heavy, heavy, light of this correlator, for example, huge, huge, heavy, is something that Arish has unpublished work with Volodya and Volodya's student. You can ask him more.
Okay, let's thank Pedro for the very beautiful talk.
Thank you.
So Yiming Chen will be next.
Hello. Can someone go to my slides? Okay, so I would like to first thank the organizers for giving me the opportunity to present my work today. So my talk will be based on a very recent paper with my wonderful collaborators, Yiming Chen, Bisong Xie, and Zhenbin Yang. 2 of them are in the audience. Let me begin my talk with a little bit of motivation. So the horizon of a black hole is a ubiquitous feature of classical general relativity. Through holography, we've learned many of its quantum signatures, such as thermalization, scrambling, random matrix statistics, etc. Now, these very universal features of black hole microstates are usually sharpest in the n going to infinity limit of the boundary theory. Today, my focus will be on a new feature that is called fortuity, which was proposed by Chang and Lin based on this earlier work here, which reveals some curious finite n features of black hole microstates, specifically in the case where they are supersymmetric. Now, we've already heard about this notion of fortuity and its opposite, monotony, from Yiming during last streams, but let me begin with a short review. I will focus on the case of n equals to 4 super-Young-Mills theory for concreteness. Now, here, an important role is played by these so-called trace relations. These are finite n identities which relate multi-trace operators in the theory which were independent in the n equals to infinity limit. So here, I'm just showing you a simple example of a trace relation when n is smaller or equal to 2. Now, with these trace relations, heuristically, one can classify the supersymmetric states in the theory by how they are annihilated by the supercharge Q. For example, the monotonous states are defined as those states or operators that are directly annihilated by Q without using any trace relations. On the other hand, the fortuitous operators are those that when you act the supercharge Q on them, you get an expression that is not manifestly zero, but becomes zero when n becomes small enough, here smaller or equal to some critical value that I denote by n star, due to these finite n relations. Now here I'm being very heuristic, but this idea can be formulated precisely in terms of Q cohomology and the long exact sequence. Now a very nice way to see fortuity is discussed in this nice paper by Pedro et al. Well, they propose to follow the spectrum of the theory as functions of n by viewing n as a continuous parameter. So that is what I'm doing in this plot here. So if you look at this plot, the vertical direction is the energy of the states, and the horizontal direction is n. So in this plot, we are tracking the energy of 3 non-BPS states, as well as 1 BPS state, which in this case is monotonous. So since the state is always annihilated by the supercharge, it is BPS no matter what the value of n is. Now we know these families of BPS states very well. In the n going to infinity limit, these states are multi-graviton BPS states that are excitations around the ADS vacuum. Now when n becomes smaller while fixing the charges, these states, they are not black holes, they become these huge operators that Pedro mentioned in the previous talk, and various evidence suggests that they actually correspond to microstates of horizonless geometries. Now, the fortuitous states behave very differently when you do this. So because when you act the supercharge on them, it is not zero when n is large. They are actually non-BPS and have non-zero anomalous dimensions. Their anomalous dimensions following this red line only vanishes when you reach the critical value of n. So in some sense, these states, even though they are BPS, from this following n point of view, they already have a non-BPS origin. And from index counting argument, we know that the entropy of such states matches with the black hole entropy in the 1/16th BPS sector. So these are the states that are responsible for the black hole microstates. Good. Now, because of these differences, our understanding of monotonous states versus fortuitous states are on very different footing. We know all the monotonous states, or more precisely, the representative of cohomologies, in the n equals 4 super-Young-Mills theory from an old paper by Chang and Shi. However, the study of fortuitous states has so far been quite limited to small values of n. So here I listed some references which explicitly study these states or cohomologies when n is equal to 2 or 3. So finding them in n equals 4 super-Young-Mills theory is very difficult. It involves laborious numerics and, in some cases, hard guesswork. And the general emerging features of these states in the large n limit is still quite mysterious. So that's what I want to focus on in this talk, is to trying to understand this phenomenon of fortuity better in first toy models, and we will extract some universal lessons. Good. Luckily, we don't need to go very far away to find such a toy model. So the first toy model in my talk today will be the so-called n equals to 2 supersymmetric SYK model, which has already been studied by these authors listed here. And it is a very simple model of a quantum mechanical model with n complex fermions given by this anti-commutation relation. written here. Now the model is defined as following. So you first write down its supercharge, which is defined as a sum over products of Q fermions. So you have some product of Q fermions weighted by some random coefficient C. Now this C is some random number that you draw independently from some Gaussian, complex Gaussian ensemble. And the Hamiltonian of the model is simply defined as the anti-commutator of Q and Q dagger. So therefore, later when I say BPS states in this model, I simply mean the zero energy ground states of the model. A nice perspective of the supercharge is to think of it in terms of a random Q form. The reason is, since the fermions anti-commute, we can choose the coefficients to be a fully anti-symmetric tensor. Therefore, we can think of the supercharge as a Q form. But this language will be useful in the later discussion. Now, before I jump into the detail, let me review a little bit about the properties of this model. So it's a nice toy model because it's solvable in the large N limit using mean field techniques. Now, the model is known to contain an extensive amount of zero energy states. By extensive, I mean that the entropy of the BPS states grow as N. So this seems to be a good place to try to look for these fortuitous states. Now, another important aspect of the model is that the low energy dynamics of the model is governed by a universal effective theory called the Schwarzian theory. More precisely, the n equals to 2 version of the supersymmetric Schwarzian theory. This theory has been proposed by various authors to be shared by various higher dimensional near BPS black holes. Now let's finish setting up the stage. First of all, we notice that the Hilbert space of the model can be graded by the R charge, which in this case is simply the number of fermions. And the arbitrary state with R charge equals to P, meaning containing P fermions, is given by this expression. So it's some P fermion operator acting on the Fock vacuum weighted by some coefficient, which again can be thought of as a P form. With all this set up, the underlying cohomology problem is very simple and quite elegant. So let's see, when we act the supercharge Q on a P form, which is denoted by alpha P, it takes us to a P plus Q form that is simply equal to C wedge alpha. And when we try to find BPS states, which are in one-to-one correspondence with BPS cohomologies, we want to find the P forms that are Q-closed, meaning that those that are, when you wedge product with this C form, you get 0, modulo the equivalence relation, where two forms are identified when they differ by a Q-exact form, which are those that can be written as C wedge some other form. Good. Now with all this set up, we can ask where are the BPS states in this model? So let's first make one observation, that is, if we keep fixed P and take N to infinity, then the map from the P form to P plus Q form look schematically like the following. So it looks like a very, very, very long rectangular matrix with a number of rows given by the number of P forms that scales as N to the P, while the number of columns scale as N to the P plus Q, which is much larger in this limit. And this matrix has these random coefficient C's sprinkled here and there. So with generic coupling C, meaning that C's that do not carry any extra structure, we expect such a matrix to easily saturate its possible rank, just because there are so many more columns, different columns, compared to the number of rows. And what is the possible rank of this matrix? The possible rank is almost the number of rows up to the small trivial kernel that is this matrix is constrained to have, meaning that those states that are Q-exact, or those forms that can be written as C wedge some other form. So that is a trivial kernel that is forced to have. Now, in summary, this implies that in this limit with fixed P and N going to infinity, this matrix does not have additional kernel, meaning that there are no BPS states. We can apply a similar argument for the Q dagger, and that would suggest that there are also no BPS states when N minus P is some order 1 number. So in this plot, I'm showing you the number of BPS states or the dimension of the BPS subspace as a function of the degree p, and we simply see that there are no BPS states at both ends. Now, somewhat strikingly, by exact diagonalization of the model, it reveals that, in fact, all the BPS states are extremely concentrated. They are concentrated in an extremely narrow window near the center. So here, let me just show you the result with Q equals to 3, when the supercharge contains 3 fermions, and when n is even. So in this case, we only find BPS states when P is equal to n over 2 or n over 2 plus minus 1. So not only we don't have BPS states near the end, we basically don't get them until we reach the center. Now we can further refine this discussion that I told you with an additional ZQ charge in the model that is invariant under acting with Q. This ZQ charge is defined by R charge mod Q. And the purpose of that is that once you've done that, these 3 different charge sectors actually have different ZQ charge. So with fixed ZQ charge, the statement is very simple. Only a single charge sector contains BPS states. Now this phenomenon of all the BPS states being concentrated in a single charge sector, we think is quite sharp. So we made a name for it. We call it R charge concentration. Now in SYK models, it turns out to be a highly robust feature. You can try to defeat this feature by making the couplings non-generic. For example, by making it very sparse, pruning the coupling such that it only has a small number of non-zero components. But it turns out that for the R charge concentration to fail, you basically need the couplings to be vanishing. We quantify this in our paper more explicitly. So it's a very robust feature. Now let me come to the first implication of R charge concentration phenomena, which is that it implies fortuity in a natural way. So here, what I'm showing you is the R charge of the concentrated sector as a function of n. And we can read this plot in different ways. If we read it in the vertical direction, that is basically the R charge concentration that I was mentioning, that if you fix the theory and vary the R charge only in one charge sector, you get BPS states. But we can also read it in the horizontal direction. Now here, if we follow the blue arrow, what happens is that at large n, there are simply no BPS states. And as we decrease n, at some critical value, one should suddenly encounter an exponential amount of BPS states. Therefore, from this following n picture, we know that all these BPS states must come from the non-BPS subspace. They are all fortuitous. Now, by further decreasing n and reach the other side of this red line, we simply find that these states must exit the BPS, the Hilbert space, pretty soon. In other words, they cannot survive for very long. The way that they disappear from the Hilbert space is by quickly turning into these trace relations. Of course, I didn't emphasize this aspect in our discussion, but there's also the analogy of the trace relations in SYK models, which are essentially any P forms with some component whose index takes value that is greater than n. Then this would be the analogy of the trace relation. Good. Now, this picture of following n and study fortuity can be fleshed out very explicitly in SYK models. Here I'm just showing you some plots, but I don't have time to tell you about it. But please ask me later if you are interested. Now, let me go to another aspect. Let me go to another aspect of the R charge concentration phenomena, which is the connection to the Schwarzian theory. Now, from the effective theory point of view, R charge concentration is consistent with the prediction from the super Schwarzian. It was shown by Stanford and Wheaton that by quantizing the n equals to 2 super Schwarzian theory, they found that all the BPS states, at least in the large n sense, are concentrated within a narrow window given in terms of the infrared R charge as seen by the Schwarzian. Now, therefore, we see that there is this interesting connection between the fortuity of supersymmetric black hole microstates and this Schwarzian description. let me make some speculations and comments on this, our discussion and the so-called nonlinear charge constraint in the literature. Now, in many cases, it is observed that supersymmetric Lorentzian black hole solutions only exist when their charges satisfy a non-trivial constraint. For example, here I'm showing you the case in ADS5 that various charges of the black hole have to satisfy this equation for you to find gravity solution, supersymmetric black hole solution. Now, since this is an equation that is derived from gravity, most conservatively, you might interpret it as a coarse-grained statement, meaning that in the two-dimensional plane of the R charge and n, within some band, some coarse-grained region, you can have large number of BPS states. But perhaps from the microscopic theory or from the near-horizon ADS2 region and its Schwarzian description, the minimal picture is really that the theory exhibits R charge concentration, meaning that this equation is merely an approximation to a much sharper constraint in the microscopic theory. When you fix n, only one charge sector contains BPS states. Now, of course, the actual story in n equals 4 superyoung mules theory is much more complicated. So here, let me quickly go through some of the subtleties. For one, the theory contains monotonous states that do not concentrate. But for our purpose, let's just focus on these fortuitous states. It was also taught to us by Shiraz from last strings that there exist other supersymmetric black hole solutions which you can get by dressing these pure black hole solutions, by either dress it by some graviton gas far away or by wrapping it with some dual giant graviton. So that might naively suggest that you might have a complete two-parameter family of solutions on this two-dimensional plot. However, there are various evidences from field theory and gravity suggesting that this dressing that you can dress the supersymmetric black holes might need to carry large enough charge in order for you to get new BPS solutions. So it's tantalizing to suspect whether such a phase diagram might be true, that at least near the vicinity of these pure supersymmetric black hole solutions, they indeed exhibit R charge concentration. It would be good to understand whether this is true. Okay, let me come to the second part of the talk. The motivation is that the ordinary supersymmetric SYK model do not contain monotonous states with generic couplings. We would like to have a model with both fortuitous and monotonous states so we can compare their properties. Now, we achieve this by generalizing a nice two-flavor model of Heeyeon to Ricci and Zhao. Well, in their model, there are both precise and chi fermions, and so the supercharge takes the following form. For convenience, I'm taking the chi fermion to be an annihilation operator. Now, this model also has a large number of fortuitous states. They exhibit this R charge concentration phenomena, etc., which illustrates to many of the previous points that are being made. But here, let me focus on how to get monotonous states in this model. So the idea is that you can arrange these couplings,Cijk, to have some additional structure. For example, the simplest case is that you can symmetrize it with respect to the last two indices, J and K. Once you've done that, the model is forced to have such an operator V, which I like to think of it as the analog of graviton operator in n equals 4 superyoung mules. This is an operator V that always commutes with the supercharge Q, no matter what the value of n is. Okay, and what is this V? This V is simply a fermion bilinear operator, psi chi with the index contracted. Once you have this operator, you can then construct a tower of monotonous states by acting this operator V several times on the Fock vacuum. Now, in our paper, we discuss why these states are monotonous, but here let me just emphasize the intuition. Intuition is that these states only depend very weakly on n. The only dependence on n is essentially hidden under this range of summation from 1 to n. And if you ignore that, then these states do not depend on n. That's the intuition why they are monotonous. Now, we can further generalize in the model such that it has multiple such graviton operators, V1 through Vk. And you can form larger or heavier BPS states by taking products of them and acting on the Fock vacuum. Let me mention some properties of them. One is that the number of such monotonous states is much smaller than the number of fortuitous states. They grow only polynomially in n instead of exponential growth of the fortuitous states. Now, these states differ from the fortuitous states. They are controlled by some interesting underlying algebraic structures. So we found that in our model, these states form representations under some symplectic groups. Now, one might worry that once you've introduced structure in the coupling, maybe you can't solve the model anymore. That is actually not true. So we found the model is still solvable in the large n limit. And interestingly, the existence of this small number of special states do not modify the large n properties of the model too much. The model still have these fortuitous states that are governed by the same solutions. Now, once we have this model, can we provide some further evidence for the connection of fortuity with the emergence of horizon? In particular, we want to ask how does the distinction of fortuitous versus monotonous get relayed to other universal features of black hole microstates, such as chaos? So this is what I will comment on in the last part of my talk. Now, in the BPS subspace, the usual notion of chaos does not work. So the usual notion in terms of the level repulsion between energy levels does not apply because all the states have the same energy. However, we can still study a notion of so-called BPS chaos, which is the notion of whether the BPS subspace resemble a random subspace with respect to simple basis in the Hilbert space. Now, for instance, one can take the simple basis to be some eigenbasis of simple operators. In a previous paper with Henry Lin and Stephen Schenker, we explored this idea of BPS chaos of various monotonous or horizonless subspaces in field theories, including the n equals to 4 CP Mills theory and D1, D5 CFT. There, what we verified is indeed these monotonous subspace, they do not exhibit the extent of randomness one would expect for black hole microstates. However, our previous discussion was cut short in the fortuitous case simply because we cannot access enough of them to perform the same similar calculation. But we can do a much better job in the toy models. So without going into the detail, let me just report to you that we've performed several checks of this BPS chaos in our model using different kinds of probes as listed here. And they all suggest that the monotonous states in our model do not resemble random states, while the fortuitous states do. The non-randomness of these monotonous states is quite intuitive from what I told you. There are these fermion bilinear operators, product of them, acting on the Fock vacuum. So this kind of states obviously is very different from generic random states. However, the fortuitous subspace is much harder to describe explicitly to you. So here, let me just tell you one perspective of understanding their randomness by this following n picture. So we naturally expect them to display similar randomness as generic non-chaotic BPS, generic non-BPS states, chaotic non-BPS states. So the idea is that in this following n story, we can not only follow the energy of the states, but also imagining following the wave function psi of the state. And if we assume that the non-BPS states are highly random, they are chaotic, then through following n, they carry this randomness into the BPS subspace. So in a way, we can say that the BPS subspace gets invaded by this randomness from these non-BPS states through the phenomenon of fortuity. While this does not happen in the cases without fortuitous states. Now here, this is a qualitative picture, but in SYK models, we verify this picture quantitatively. Okay, let me end my talk with a few future directions. Now, this R-charge concentration phenomenon plays an important role in our story and connection to fortuity. It's interesting to ask whether it's a universal feature for generic Q local supercharges. We found that in SYK they do exhibit this phenomenon, but whether we can wonder whether it's a more general phenomenon. In particular, there has been this interesting discussion by Turiachi and Wheaton about constructing supersymmetric random matrix ensembles. It would be interesting to understand whether these special members that exhibit R-charge concentration all the BPS states concentrated in some specific outcharged sector play a special role in that discussion. Along the same line, I think this outcharge concentration phenomena is a good way to test Schwarzian from the first principle in field theories. Now the reason is because, different from some other features, this feature of outcharge concentration, we expected to see even at moderate n, some small value of n, and weak coupling. So that makes it a very ideal target for the study of BPS cohomologies in these models. Now, finally, we would like to ask how to generalize these lessons about fortuity away from BPS. Perhaps there are some more general lessons one can learn. So here I'm just asking some questions which might help in this direction. For example, as we've seen in this fortuity story, the fortuitous states depend extremely sensitively to n. For example, if we just change n by 1, we can go from no BPS states to an exponentially large amount of BPS states. Now, can we understand this extreme sensitivity to n from the gravity point of view? And a related question is, what is the gravity interpretation of these trace relations, these null states that appear in this fortuity discussion? And with these questions, I'd like to thank you for your attention.
Okay, questions? Kumran?
Thank you for a very nice talk. So if you take SUN, n equals to 4 Yang Mills, and replace SUN with SUN plus K slash K supergroup with same n equals to 4 Yang Mills, that's presumably, we don't know if that theory really exists or not, but as far as if it exists, it's a non-unitary theory of some sort. But all the monotonous operators for that theory and the SUN n equals to 4 Yang Mills are identical. So their only difference is in the operators that you have been studying. So the question is whether or not you can, first of all, extend your operators by not just SUN, but a K, which is the label of SUN plus K slash K, which give you different trace relations. And how do you see unitarity as being restricted to a particular fortuitous states that you have for SUN, but not for SUN slash K versions? In other words, somehow the notion of unitarity is embedded in it and distinguishes between unitary and non-unitary theories like SUN plus K slash K.
Right. I guess the first question is if you want to also discuss this following n story, there, as you said, you have two parameters now, yes, both n and k.
Yes.
So you can decide to either fix one and follow the, let's say, fix k and follow n, then I expect the story might be similar. But I don't know whether there will be an interesting story with fixing n and vary k.
But it would be interesting to see if k non-zero gives you something bad. In other words, the non-unitariness should be something there when k is non-zero.
Yes, of course. Yeah, if the theory is non-unitary, then this following n story might also be different if the energies are complex instead of real. Yeah, it would be interesting to see.
Thank
you. Edward?
I was wondering what happens to a generic fortuitous state if you make n smaller. Naively, once a fortuitous state appears at n equals n star from some trace relations, it would persist for all smaller n because the same trace relations are true. But when you reduce n, there should be far fewer BPS states.
Yes.
So I suspect that a generic fortuitous state becomes 0 when you make n star 1 smaller.
Yeah, that's exactly true. So maybe I was a little bit fast on this slide, but that was what I was trying to comment on. So if indeed there is this phenomenon of R-charge concentration, then as you go to the left of this red line, you should immediately end up with 0 BPS states, in fact. So for the sake of argument, let's say the red line has width that is equal to 1. Then these states should immediately all become trace relations and should disappear from the Hilbert space.
So that's an expectation or in gauge theory, or is there some calculations showing that happens?
In the SYK case, we can show this explicitly happening. Yeah. In the gauge theory case, it's an expectation from this Schwarzian description.
It would be interesting to compare n equals 2 and n equals 3 and show that most of the n equals 3 states are trivial at n equals 2.
I agree, yeah, that would be interesting.
Question there?
Are you closer to having an understanding of what generalizes the notion of trace relations in superconformal theories without a Lagrangian description?
So I guess one way to think about fortuity without really making this connection to trace relation explicit is from this following M picture. So I think even in theories without Lagrangian description, one might still be able to do that as long as you have a continuous central charge to play with. But in terms of how to think about trace relations explicitly, I don't have immediate comment.
Okay, let's thank Yiming again for a beautiful talk. Next is Heeyeon Kim.
Thanks a lot for the invitation. It's an honor to be able to speak at this wonderful conference. So this talk is going to be a summary of a program that I have been pursuing in the last couple of years concerning rational vertex operator algebras from supersymmetric field theories, which is based on various collaboration with many collaborators that are listed here and also partly related to the work by other people that I wrote there. To begin with, a rational vertex operator algebra is an algebraic structure that describes the 2D rational conformal field theories. And 2D RCFT is probably the most well understood class of conformal field theories, which are characterized by the fact that the Hilbert space decomposes into a finite sum. And the representation theory of the rational vertex operator algebra has been studied extensively since probably 80s. And it's known that it gives rise to the structure of the modular tensor category. And an important structure is that the existence of the 3D semi-simple topological field theories that we can associate to every rational vertex operator algebras. And in this picture, the space of conformal blocks of 2D theory can be identified with the Hilbert space of 3D topological field theories. And the most important properties that's going to be important in this talk is the fact that the only local operators in the semi-simple TFT is in identity. Probably the most well-known example is the Chern-Simons theory in the bulk. In the 3D theory, we have a Chern-Simons theory, and then you can impose some holomorphic boundary conditions on the 2D boundary. And there are some local operators induced in the boundary that forms a singular operator product expansion that forms a 2D vertex operator algebras, which can be thought of as a chiral Westermann-Witten theories. So for unitary theories, those Chern-Simons theories and Westermann-Witten like theories on the boundary can be thought of as some sort of a building block so that everything can be reduced down to the Westermann-Witten type theory or their coset constructions. But for non-unitary rational vertex operator algebras, such an explicit topological field theory descriptions or some explicit constructions for this 3D, 2D system is not very well understood. Even for the simplest class of examples, such as a generic Virasoro minimum models, we don't really have a complete picture of this. So there is an interesting way to obtain a large class of 3D topological field theories from the supersymmetric quantum field theories. So you start from the 3D quantum field theory with n equals to 4 supersymmetry, then you can perform a full topological twist. So for a given 3D n equals to 4 theory T, you can find two nilpotent operators, say QA and QB. And by passing to one of the cohomologies with respect to those QA or QB, you obtain a pair of topological field theories that I call TFT-A and TFT-B. And the TFT-B corresponds to the Brzezinski-Witten twist, And then TFT-A corresponds to the dimensional reduction of the Donaldson's twist since for the n equals to 2 theories. Now that we have a 3D topological field series, and these 3C series can be put on a half space with 2D boundary as before, with some choice of holomorphic boundary conditions, which is chosen in a way that it's compatible with the twist that you made in the work. Okay, sorry. So the algebra of the local operators that are induced in the boundary also form the structure of the vertex operator algebras. However, the problem is that, or the interesting aspect of this is that the generic vertex operator algebras from these constructions in general are not rational. This is because of the existence of the local operators in TFT-A or TFT-B, which is originally come from the Coulomb branch operators or Higgs branch operators of the 3D n equals to 4 theory. These are the operators by definition that passes the cohomology of the QA or QB. So this leads us to think about the two very important necessary conditions for those TFT to admit a rational vertex operator algebra in the 2D boundary, which is the fact that first, there must be a zero-dimensional Coulomb branch, and second, there must be also a zero-dimensional Higgs branch. And these are SCFT that we call rank 0 SCFTs. But it's in general difficult to construct such a rank 0 SCFTs because it's believed that they are all non-Lagrangian, in the sense that there is no Lagrangian description that preserves the full n equals to 4 supersymmetry. But what's nice about it is that it often admits a simple UV gauge theory description that only has an n equals 2 supersymmetry, which is then expected to flow to an n equals to 4 rank 0 fixed point in the IR. So the first example was constructed by Gang and Yamazaki in 2018, which is called a minimal rank 0 SCFT. It's called T-min. It has a very simple gauge theory description that has an n equals 2 supersymmetry. It's a U1 gauge theory, level 3.5, coupled with 1 chiral multiplet. And you can find various indirect evidences that this theory in fact flows to a rank 0 fixed points with zero-dimensional Coulomb branch and zero-dimensional Higgs branch with supersymmetry enhancements to n equals to 4. So this is an n equals to 4 theory, the IR theory. This T-min theory can be topologically twisted to produce a pair of topological field theories out of it, which are expected to support some rational vertex operator algebras on their boundary. And it was originally conjectured in this paper that this T-minimum theory indeed supports the Virasoro minimal model, the simplest non-unitary Virasoro minimal model M2,5, which is sometimes called Liang model on the boundary. And you can in fact do some explicit OPE calculations of this theory, the T-min theory. But the calculation of the boundary OPEs of this theory is not straightforward because the theory that you start from doesn't have a Lagrangian description, and also without Lagrangian description, the description of the topologically twisted theory is difficult. But you can explicitly calculate the OPEs for this example by introducing a technique called the two-step twisting. So in this technique, that you first perform only a partial twist, the holomorphic topological twist of an n equals to 2 theory, and then you calculate the boundary OPEs with this holomorphically topologically twisted theory. And then at the level of the OPE, you can track down the process of deformation to the full A and B twist. And you can show that if you just focus on the TFT-B, if you impose the Dirichlet boundary conditions on the boundary in a supersymmetric way, you find that there are 5 operators that are survives on the Q cohomology on the boundary. The J is the U1 current operator. V plus minus are boundary monopole operators, and theta plus minus are some fermionic operators. So you have 3 bosonic and 2 fermionic operator, or have conformal dimension 1. And you can show explicitly that their OPEs given fine linear support algebra, OSP 1/2 at level 1. This is a simplest example of the non-unitary rational vertex operator algebra that has a current. The relation between this affine VOA and the originally conjectured Virasoro mineral model M2,5 is level rank duality. And you can, in fact, show that these two are related by the level rank duality in the sense that the category of the modules of two VOAs are equivalent to the orientation of reversor. And in this particular case, this level rank duality also can be understood from the mirror symmetry of the 3D n equals, original 3D n equals to 4 SCFTs. So this is all good, but it's very difficult to go beyond this example because the construction of the rank 0 SCFT, you have to rely on some accidental supersymmetry enhancement, and it's very difficult to predict from the UV gauge theory point of view. So the natural question here is that, is there a more systematic way to construct a rank 0 SCFTs? So we can get some insight from the 2D RCFT classification program. There are a few different approaches to this classification program of 2D RCFTs, but the overarching theme is the modular invariance there, which makes use of the property that the characters of irreducible modules in 2D RCFT transform as a vector-valued modular forms. There are a finite number of chi's that transform in that way, where S and T's are there's some finite dimensional representations of SL2Z. And each of these characters, chi alpha, also transforms as the modular function under some congruent subgroup of SL2Z. So the first approach is using the modular linear differential equations, which makes use of the fact that those chi satisfy certain class of modular linear differential equations, which goes back to the work of Muki and San in 88, which we will come back to at the end of the talk today. Slightly less well-known way about classifying such a 2D RCFT is by what's called the NAMS conjecture. And this is more relevant to my talk today. So it starts from the observation that a large class of RCFT admits a character that's written in that particular form. It's called the NAM sum type formula. Okay, where the A in the numerator of the exponent is some square matrix, and B is a vector, and C is some rational number. It's known that a large class of RCFT characters take this particular form for some choice of A, B, and C. The natural question here is, for which A, B, C does this function chi become a modular function and therefore a candidate of the RCFT characters? Okay. Interestingly, this problem is closely related to some properties of the logarithm evaluated at certain algebraic numbers, which is related to NAMS conjecture. And in the paper by Zagier, those ABCs has been classified. The ABC that solves this problem has been classified for, say, R equals to 1, 2, 3. The main observation for this work is that this NAM sum formula that I mentioned in the previous slide also appears as a half index of an abelian 3D n equals to 2 theory with certain choice of boundary conditions. Okay, so this chi ABC that I mentioned in the previous slide can be thought of as some sort of the partition function computed on the background of disk times S1, which you can argue that coincides with the vacuum character of the boundary algebras of the 2D theory. And this motivates us to turn this particular problem into a problem in physics to classify the IR phases of the abelian Chern-Simons matter theories. So you consider that n equals to abelian Chern-Simons matter theory is labeled by the label matrix K in the matter representation Q in some superposition W. And in order for such a theory to admit a rational vertex operator algebra in the boundary, there are two possibilities. The first possibility is that it flows to the unitary TFT, so it supports a unitary rational vertex operator algebras on the boundary. The second possibility is that it flows to n equals to 4 rank 0 fixed point, so that you can make a topological twist to the TFT A or TFT B, so that it supports some non-unitary rational VOA on the boundary. So in this work, we scanned over all n equals to a large class of n equals to Chern-Simons meta theories with this particular representation and search for Lebesgue matrix K that admits the superpotential deformations, so that theory flows to rank 0 fixed point. And then we find that there exists, for r equals to 1 to 3, as in the paper by Zagier, we find 28 sporadic K matrices, along with some several infinite families. And we find that this result reproduces and also slightly generalizes the analogous search for the modular Namsan formula that I mentioned before, classified in the paper by Zagier. And these are the theories that flows to the rank 0 type of theories that can be topologically twisted to produce a semi-simple topological field theory that are not of Chern-Simons type. And you can argue that these theories support indeed various rational vertex operator algebra that I listed here. So the most simplest class of examples are Virasoro minimal models of this following type, and also some super Virasoro minimal models, and finally super algebra of OSP1 size 2n type. And you can also find some examples of minimal W algebras from these constructions. One interesting observation is that many of those rational vertex operator algebras that I constructed from 3D rank 0 SCFT type theory also appear in the celebrated 4D equals to SCFT and VOA correspondence. So in this paper, these gentlemen constructed a precise map that gave rise to a 2D vertex operator algebra for a given 4D equals to SCFT. So for example, this example, the Virasoro, this particular class of Virasoro minimal model that I mentioned in the previous slide, appears as an image under this map if you consider the simplest type of non-Lagrangian Argyros-Douglas theories. The natural question here is, what's the precise relation between these two constructions? The answer is the cigar compactification. It actually goes back to the old work of Cecotti, Naitsky-Bappa in 2010, and it also has been recently revisited by the Dushenko in the more in the context that I'm discussing today. When you consider the 4D n equals to 2 supersymmetric conformal field theory on a holomorphic topological twist background, so you consider R2 times R2 times C, and on R2 you perform a topological twist by the U1R symmetry, and you put the theory on a Sigal-like geometry by performing an omega deformation. And the operators that are localized on a cigar, the tip of the cigar, they form a non-trivial VOA on that VOA plane, the plane C. And the compactification along the cigar circle, the S1, the red circle above, give rise to the our 3D 2D system where the tip of the cigar now becomes the boundary of the 3D theory. Now what's interesting is that because of this U1R twisting that we are making in a topological plane, on the cigar side, it involves a non-trivial 2 pi rotations of the U1R symmetry along S1. So of course, this is a 2 pi rotation, so this twisting, extra twisting is trivial for the Lagrangian type theories where all the Coulomb branch operators have integer R charges, but this extra twisting is non-trivial for the theories that contains the Coulomb branch operators that has a fractional R charges. Okay, so in particular, these are non-trivial for Argyros-Douglas type theories. So this twisted compactification with an extra twisting by the U1R symmetry can be most easily understood in terms of the Coulomb branch perspective to the 4D n equals to 2 theory. So this picture is a U-plane of some Coulomb branch of the 4D n equals to 2 theory. And you consider a closed path in the Coulomb branch that I draw with this black line. And these are parameterized by x3, the coordinates of the compactification circle. And in order to realize the U1R twisting that I mentioned in the previous slide, you require that as you go around that path once, the central charges also make a continuous 2 pi rotation around it. And in particular, this path can be chosen to be homotopic to the Janus-like configuration of the effective abelian gauge theory, parameterized by the varying coupling constant, which is determined by U of x3. This can be chosen to be preserved to 3D n equals to subalgebra. And there are 4D BPS particles that satisfy the set trace of BPS conditions. And these 4D BPS particles can also be 3D BPS particles if it also satisfies the condition of the 3D BPS bounds. And if that happens, the 3D BPS particles are going to be trapped at the particular location. And this equation is satisfied only on certain points on this path that I described there. And these 3D BPS particles that are trapped at various points on the path are described by the 3D chiral multiplets. So those 3D chiral multiplets are locally charged under the local U1 gauge symmetries. But in order to describe this system as the full local the symmetry, we have to insert you have to insert certain dually domain words in an appropriate loci on the path so that we can obtain some effective 3D abelian Chern-Simons matter theory. And the Chern-Simons matter theory that you obtain from this description is precisely the kind of the Chern-Simons matter theories that we described in the previous part of the talk. And this picture is in fact responsible to the IR formula for the short index of the 4D SCFT, which is known to compute the vacuum character of the corresponding vertex operator algebras. So what this proposal tells us is that for a given BPS particle with this electromagnetic charge gamma, we can assign some quantum torus algebra variables and the short index, which counts the operator that passes the cohomology in the 4D n equals to 2 VOA correspondence can be computed in terms of that trace in quantum torus algebra, where this EQ is a Q exponential, and whose argument is given by the quantum torus algebra variable. And you can argue from the identities of EQs that the I sure is a work-crossing invariant quantity. And in fact, you can evaluate this trace formula and to find out that this is also something that can be written in terms of the Nam-Sum formula that I mentioned before, and from which we can construct a candidate 3D abelian Chern-Simons matter theories whose half index exactly coincides with the Schur index. So for example, the simplest Argyros-Douglas theory, we obtain this interesting IR formulas, and from this we can extract the 3D n equals to U1 to the squared Chern-Simons matter theory with a particular Chern-Simons level with 4 chiral multiplets. And using various elementary dualities like particle vortex duality, you can argue that in fact flows to the T minimum theory that we discussed in the beginning of the talk. And this analysis, in fact, motivates us to propose a more universal formula that computes the other 3D observables, for example, the ellipsoid partition functions of the twisted rank zero theory. So instead of the Q exponentials, we now use the Faddeev logarithm. The trace is the trace in some auxiliary Hilbert space where this Faddeev logarithm acts naturally. And again, this pentagon identity ensures that this SB is a work-crossing invariant quantity, and we can check this proposal for many examples of Argyros-Douglas type theories. And it's actually natural to consider, once you have this Janus loop-like picture, it's natural to consider the multiple wrapping of the Janus circle, which leads to a family of 3D theories, where this small n in the slide is how many times you wrap around the Janus-like circle. And for each n, you get a candidate of the supersymmetric observables that corresponds to each of the 3D TFTs. And if the archers of the Coulomb branch operators are fractional, as in the Argyros-Douglas-like theories, you can argue that there exists an integer n such that the nth wrapping of the Janus loop trivializes U and R twisting. And indeed, you can explicitly check that that identity, the Faddeev logarithm, the product of the Faddeev logarithm raised to the nth power is equal to 1 for all the Argyros-Douglas type theories. This gives rise to an interesting picture that for a given 4D SCFT, you obtain a family of vertex operator algebras if you start from the Argyros-Douglas type theories. So for example, for the simplest type theories, the A1, A2 theory, we obtain 4 vertex operator algebras whose modular data are related by the Galois conjugations. And for the simplest case, we obtain the M2, 5. For the second wrapping, we obtain G2 at level 1. For the third twisting, we obtain F4 at level 1. And for the fourth twisting, we obtain the OSP1/2 at level 1, as I mentioned before. An interesting observation is that the Shor index formula actually has a better convergence property if you think about the negative powers of n. And what's interesting is when n is equal to -4, this monodromy trace formula gives a modular invariant characters of this mysterious intermediate algebra called E7.5 at level 1, which was one of the missing holes in the classification of the SCFT with 2 characters in this original MLE program was conducted by Matsumoki and San. And from this observation, we can actually propose a very simple UV descriptions of a 3D topological field theory that supports the vertex operator algebra with these characters. So this is the Quiver-like diagram. So this 3D TFT has a UV description in terms of the U1 to the 8 theory. And these are interacting via the mixed Chern-Simons level given by the E8 Dinkin diagram. And there is a little the chiral multiplet attached to the first node. And this is you can check many indirect evidences that in fact flows to the 3D rank 0 SCFT that can be topologically twisted to support the vertex operator algebra with those characters of the intermediate algebras. So this is a summary. So probably my time is almost up. So I will just leave here for the discussion, and this is what I wanted to say. Thank you.
Questions? Leonardo?
Sorry, this is a simple clarification. In your last example, this E8 quiver, you can do the A twist or the B twist, so why do you get 4 theories? I didn't understand that.
No, this is one of the examples that comes from the -4 twisting. So those examples that I wrote in there is of the n equals to 1, n equals to 2, n equals to 3, and n equals to 4. And if you go to n equals to -4, it gives rise to this particular.
Oh, I see.
Yeah.
This particular quiver corresponds to n equal to -4, which is it the A or the B twist?
It's actually not easy to distinguish A and B twists because they are both moduli spaces at both points. It's one of the twists. Yeah.
It's one of the 2.
Yeah, one of the twists.
Thank you.
At some point you mentioned level rank duality and mirror symmetry for the rank 0 cases. So what do you mean by mirror symmetry for rank 0?
The mirror symmetry that exchanges the Coulomb and Higgs branch. So in this case, the mirror symmetry that exchanges the A and B twist.
The twist.
Yeah, but this particular theory is a self-mirror theory. So you get so you can actually argue that this T-min theory is mirror dual to its own orientation reversal. So its mirror algebra is going to be realized at by looking at the other side of the boundary. So this is how it realized the usual level rank duality. You have the top 3 topological field theory, and then you have 2 different boundary conditions. And these 2 are the 2D vertex operator algebra that fits in some a bunch of free fermion algebra that realizes the level rank duality.
Any more questions? Clay?
Hi, you talked about assigning abelian Chern-Simons theories from 40n equals 2 theories, where you get sort of 1 chiral multiplet for each PPS state. Can you do formally something similar in the weakly coupled limit of 40n equals 2 theories? What is that? What would you say about that?
So what do you mean the weakly coupled limit? So we
In the weakly coupled chamber of a 4D n equals 2 theory, like a SU2 Seiberg-Witten, but in the phase where it has infinitely many.
Yeah, so this can be done in a chamber where we have a finitely many hypermultiplets only. So usually it picks up the particular chamber of the theory. So otherwise, I don't know how to make this statement more precise. In general, it's gonna, for example, the SU2 example is gonna contain like infinitely many the hypermultiplets, and then assigning the 3D theory to that is not straightforward. This is particularly for the chamber that contains only finite many hypermultiplets.
Okay, let's thank Heeyeon again for the beautiful talk. And we meet again after lunch at 2:30.